lesson, we will talk about standardizing with z-scores. So we just talked about the empirical rule and how it's absolutely wonderful when you're 1 standard deviation or 2 standard deviations away, and we were able to find the probability of something happening or the chances of something happening based on the normal model. But in the real world, let's face it, most of the time you're not going to be exactly 1 or exactly 2 standard deviations away. So now what? Well, now, again, assuming that we're dealing with a normal model, and again, we'll talk more about those assumptions when we move forward through the class, but assuming it's fairly unimodal and symmetric, we're going to find something called a z-score. Now, we talked about how to shift and scale the center, multiplying, adding a constant, etc. Essentially, that's what is going to happen here, is we're going to shift and scale the center so that our mean is 0 and our standard deviation is 1. So essentially, it turns it into a normal model with a mean of 0 and a standard deviation of 1. So that's what we're going to deal with. A z-score basically takes your data and then it finds, based on 0 and 1, how many standard deviations above or below the mean is your value. Here's how we find it. To find the z-score, we're going to take our observed value, observed being whatever value we're trying to find the score for, minus the expected value. Now, our expected value is our mean. Statistically, we call that the y bar. We're going to divide it by the standard deviation, which of course is s, the standard deviation of our sample. Before we actually find these, I want you to understand exactly what it means. If you get a z-score of 1, that means you're 1 standard deviation above the mean. A z-score of -1 means your score is 1 standard deviation below the mean. If you have a z-score of 0, that means your score is exactly the same as the mean because there's no difference between your value and the mean. Most values fall within 2 standard deviations of the mean. Again, remember, 2 standard deviations was that about 95%. Anything more than 3, remember 3 was that 99.7% of data. So anything more than that, it's considered extreme. So keep that in mind moving forward. Again, I'm reminding you, this is only if we have a nice normal model. So here's how we might use z-scores. Betty took my MA 101 course, which is intermediate algebra. She received an 87% for the class. The mean percentage, so the average percentage in that class, was 80% with a standard deviation of 6. Horace also took MA 101, but with a different instructor. Different instructors grade differently. He received a 90%. For the class, the mean was 84% with a standard deviation of 5.2. So what I'm going to do is I'm going to find the z-score for Betty and for Horace. So for Betty, my z-score is the observed, which is her score of 87, minus expected. I'm expecting everybody to get the average, which is 80, divided by the standard deviation, which of course is 7 over 6, which is 1.1616, etc. For Horace z-score would be observed, which is 90, minus expected, which is 84, divided by the standard deviation of 5.2. Now again, looking at those values, Betty had the z-score that we talked about. Horace had 1.154. So even though Horace actually got a little bit better grade than Betty did, if we're actually comparing apples to apples, we're saying Betty's score was a little bit more standard deviations above the mean. So she scored better in relationship to her classmates. So it doesn't change her score, that her score was 87 and his was 90. But if you're standardizing them, if you're looking at them comparative to one another, Betty actually did better overall than Horace did. I would like for you to determine if John or Cliff are better jumpers or throwers than the other. So try that and then press play to check your work. Again, for John, we're doing the z-score. Let's try that again. Again, for John, looking at the z-score is observed minus expected. So observed is 66 feet minus expected, which was 60 feet. So that's the mean is the expected. Standard deviation is 2, so that is 6 over 2 or 3. So that means John threw 3 standard deviations above the mean, which means John is a pretty darn good shot put thrower. Cliff jumped 27.3 in the long jump. 27.3 is a little bit hard to deal with because we're dealing with feet and inches and not just inches, because the standard deviation is in inches, the mean, we're just going to turn everything into the same format. So 27.3 turned into 327 inches. 26, again, just times 12. That turned into 312. This one was 27 times 12 plus 3. So 327 minus 312 divided by 6, which is 2.5. So Cliff scored 2.5 standard deviations better than the mean, and John scored 3 standard deviations better than the mean. So John overall is better in relationship to the other throwers, shot put throwers, as opposed to Cliff and the other long jumpers.